Hello students, welcome back to Chemistry Online class, brought to you by IGHOTA Virtual Learning Platform. I am OLABISI OLAWOYE, and today I will be teaching you a topic which is Kinetic Theory of Matter. This is a carefully selected topic from the Waec syllabus, and so at the end of this topic we have questions that's been asked from years past under this topic, Kinetic Theory of Matter. So I want you to pay attention and participate during the past question revision class. Thank you. The Kinetic Theory of Matter, it's a theory that explains the properties of matter, how matter behaves and how they interact with each other. Under the kinetic theory of matter, which deals with both solids, liquids and gas, we also have the kinetic theory of gases as well. This really specify on gases, the behavior of gases. Now, we all know that matter is anything that has mass and occupies space, and it exists in different forms. The most common form is solid, liquid, and gas. And matter is made up of tiny, very tiny particles, such as atoms, ions, and molecules in them. Now, so if you look around you, anything around you has particles inside. They are made up of masses or substances inside them, and that's why they have mass. So kinetic theory of matter actually postulates that the particles of matter are continually moving and they possess kinetic energy because they are moving. Though in chemistry or in science, anytime a reaction is about to occur, if it is in solid form, the substance must change to gaseous state before reaction can actually take place. Like you have a solid of calcium tricarbonate reacting with hydrochloric acid, for instance. The calcium tricarbonate must be broken down into particles by dissolving first. When it dissolves in the solution it is, or water has been added to it, you will notice that the particles will be free, they will be loosed, and then they are in liquid state. At that point, the ions or the particles of hydrochloric acid will also react with the calcium tricarbonate. So at least the calcium tricarbonate is in a state where the particles are free to move about. So we are going to be specifying majorly on the kinetic theory of gases. And matter in the gaseous state has different characteristics from that of solid and liquid state. And the physical behavior of gases were studied by Boyle's law, Charles' law, Graham's law, and Dalton's atomic theory, or Dalton's law of partial pressure. Now, the chemical behavior of gases was also studied by Gay-Lussac, while the physical properties were studied by Boyce, Charles, and Graham's, then Dalton. So, looking at the assumptions of the kinetic theory of gases, it states the following. The first one here: the gas molecules move randomly in straight lines, colliding with one another and with the wall of their container. The second law states that, or the second theory states that the collisions of the gas molecules are perfectly elastic. Now I'm going to explain the first one. Gas molecules move randomly in straight lines, colliding with one another and with the walls of the container. It is usually or generally known that the particles of gases are loosed. That's why when you open a container of perfume at one corner of a room, it moves to another part of the room speedily, because the particles inside the perfume, which is gaseous state, which is in gaseous state or in form of vapor, even if it is in liquid form, but as long as it's being dispersed by spraying into the air, it behaves like a gas. Now, it moves faster, and it shows that their particles are free and always moving about. So if a gas is in a container, the particles are always moving, and they're always colliding with themselves and with the wall of the container. So also in liquid, the particles of liquid are always moving, colliding with themselves and with the wall of their container. It is only in solid form that the particles are still. They are held by coercive force, which makes them not to be free. Now, so the first law says that the gas molecules move randomly in straight lines, colliding with one another with the walls of the container. Number 2, the collisions of the gas molecules are perfectly elastic. Now, it shows that when these gases are colliding with themselves, their collisions are elastic. That is, they collide with themselves and also bounce back. Then, the third one, the actual volume occupied by the gas molecules themselves is negligible. That is very, very small relative to the mass, or to the volume of the container, showing that the particles of gases themselves are very, very few compared to the volume they occupy. And that's why you see that gases are always moving. They are free to move about because they have enough space for moving about. And there's something I want you to understand here. When gases collide with themselves and with the wall of the container, they're actually generating a pressure. It is this pressure that amounts to what we call vapor pressure, especially when boiling takes place. And if I'm going to show you a very good example. Assuming we have a syringe here, and then we have filled this syringe with a liquid. Now, you know, for filling a syringe with liquid, we draw it up. Can you see the space? The space is increasing. That is, the volume is increasing. Now, the liquid is in this space, and the particles are free. By the time I want to cause pressure, or I want to increase the pressure, I will decrease the volume by pressing the syringe down. And as I'm doing that, the liquid are being forced to stay in a small volume, or even if it is air or gas we are referring to here, you will see that they have been forced to occupy a smaller volume, and so that leads to increase in pressure because the particles will be moving, trying to free themselves, and then that generates what we call pressure. So that's another principle I want you to understand. Then the coercive force between the gas molecules are negligible. That is, the force that are holding the particles, the force holding the particles of gases are very, very small. So that means the gas particles are always free to move about. The last one here, the temperature of the gas is a measure of the average kinetic energy of the gas particles. That is, the temperature of a gas, when it increases, the kinetic energy of the gas particle will also increase. What do we mean by that? Now, increase in temperature increases kinetic energy. Kinetic energy is actually the energy possessed by a moving body. And so when a body is moving and the particles of that substance is moving, or a liquid particles are moving, it shows that there is an increase in temperature that has broken the particles of such liquid. For instance, now we know that liquids are made up of particles, solids are made up of particles as well, and also gases. And the particles of solid are tightly held together. Let's assume this is the particles of solid, these are particles of liquid, and that of gases, the particles are free. Now, these particles, as they are tightly held together, when you increase the temperature, the bonds holding these particles break loose and makes the particles to be free. The same thing in liquid. and at a point all of them start behaving like a gas. They are in a state of randomness, and so at that state they are moving about. That is because they possess kinetic energy, which is energy possessed by a moving body or a body in motion. So, and this is always increased as a result of increase in temperature, and that's why we say the temperature of a gas is a measure of the average kinetic energy of the gas particles. Now, using the kinetic theory to explain how melting take place. Melting usually take place in solids. A solid changes state from solid to liquid whenever there is an increase in temperature. When there is an increase in temperature, the particles, the force holding the particles of solid together breaks, and then the particles begin to move. They possess a kind of kinetic energy, and so they are able to move. And melting itself is a change of solids to liquids by the increase of temperature. That is the definition. And melting occurs at a certain temperature called the melting point. That is the temperature at which a solid melts is its melting point. For every solid has their own melting point, and that of metals is higher than that of a substance that are held by weak bond. Like in water, water doesn't really melt. It only has a boiling point. It boils. So we only use melting for solids, and there are some solids that are very soft, or they are held by weak force compared to others. For instance, now most metals have high melting point. That is, it requires a very high temperature to melt them compared to other substances like plastic, for instance. So the force of vibrations overcome the binding force anytime there's an increase in temperature. And then what happens is that the crystalline structure suddenly collapse. But there's something I want you to note. This is usually asked in Waec questions. The presence of impurities. Whenever a substance is impure, that is, it has other ions in it apart from the pure substance, it's the presence of impurity actually lowers the melting point of a solid. That is a point I want you to hold. Now, from there we move on to boiling of liquids. But before that, I would like to show you the way melting takes place in solid. The next one is boiling of liquids. Boiling is a process by which a liquid turns into a vapor when it is heated to its boiling point. When a liquid is boiled or is heated, the forces of coercion holding the particles of the liquid. I told you that liquids are held by they also are liquids as particles also that are held by forces, but the force is weaker. Now, when boiling takes place, the particles holding the force holding the particles are broken due to increase in temperature, and at the temperature at which a liquid boils is called its boiling point. So what happens actually using the kinetic theory to explain boiling? I told you that particles are always moving. That is the basis of the kinetic theory. That is, the particles of liquid, the particles of solids and gases are always moving. So when a liquid is heated to its boiling point, the vapor pressure of the liquid, that is, the particles that are moving in the liquid colliding with themselves and with the wall of the container, they generate a kind of pressure which is called the vapor pressure. This vapor pressure equals the atmospheric pressure. That is, a kind of pressure is also accrued in the atmosphere, especially in a closed container. Outside the boiling, the water itself, that is up in the space between the water and the lid of the container, there is a kind of atmospheric pressure on the liquid, and the vapor pressure too is also generated by the boiling water itself. So when these two equals each other, boiling takes place. And at that point, you will see the particles moving, colliding speedily with themselves. And this actually causes the liquid particle to gain enough energy to change from a liquid to a gas, and they form bubbles. And at this point, evaporation can take place. So I would like you to see how boiling takes place, to understand better and to see how the particles collide with themselves and with the wall of their container. Next one is evaporation of liquids. In a sample of a given substance, some particles are more energetic than the other, especially when a liquid, for instance, is boiling. The particles gain kinetic energy, and when some of these particles, some of these energetic particles, comes near a liquid surface, they break away from the attractive force of the other nearby liquid molecules, and they escape into the space above. That is, they vaporize. When this happens, we say that the liquid is already evaporating. That is, when boiling is taking place and the vapor pressure is being generated by moving particles due to increase in temperature, these particles collide with themselves, they gain kinetic energy, and the next thing is that some of these energetic particles that are more energetic than others, they break free into the liquid surface, and they escape into the space, meaning that's why you see vapor coming out from a boiling water. That's like water particles, some of the water particles escaping, and this can actually lead to reduction in the liquid that is in the container. And at this point, we say that evaporation takes place, and evaporation does not take place until the boiling take place. There must be boiling before evaporation, and evaporation can take place at all temperature. It can take place at all temperature, but anytime there's an increase in temperature, the rate of evaporation increases. Now, there is a structure that I would like you to see that shows how evaporation actually takes place. The next one is the dissolution of solute. That is, using the kinetic theory to explain the dissolution of solute. Increase in the temperature of a particle in a solvent and solute can cause them to repel each other. How? When you add salt, for instance, that's a table salt we use, you add them to water, and then you increase the temperature by stirring or by heating directly. The bonds holding the particles of the solute, that is the solid that you dissolve in the solvent, which is the water, begins to break, and there will be no attraction between the solute and the solvent, that is between the salt and the water. There is a kind of repulsion. They repel each other as temperature increases. The particles are not attracted to each other, and then they begin to separate from one another. But assuming you just add salt to a solute to a solvent, like salt and water together, and then there is no increase in temperature, the solution will be so slow. It will be slow if there is no stirring or no increase in temperature. Now, but as increase in temperature occur or stirring occur, the particles begin to separate from themselves. That is, the particles of solute and solvent, they begin to separate from themselves. And then the continuous motion of the particles in the solution by stirring cause these particles to collide with themselves. By the time they collide with themselves, this results into bonds being broken. The bonds holding the particles breaks, then attractions are being disrupted, and then the particles get separated from one another. And at this point, dissolution of solute occur. That's a state in which a salt dissolves in the given solvent. So increase in temperature brings about increase in the dissolution of solutes, and it has to do with particles colliding with themselves, breaking bonds, and being free from water. So this is actually a basis of kinetic theory of matter, in which states that matters are made up of very tiny particles, ions, molecules, and atoms, and that these particles are always moving continually, colliding with themselves and with the wall of their container. If there is no movement, there will be no evaporation, there will be no boiling, there will be no dissolution, and there will be no melting. And after this class now, I want you to pay attention to the past question revision aspect of this class. Now, these are the questions we are going to be treating. I want you to participate. Go through this question by pausing the video. You'll go through the questions on your own. Then, after which we come back, I'll pause the video too. We'll come back to solve the questions together. These are the questions. So we are going to solve these questions together after you have attempted the questions by yourself. Now, welcome back to the past question revision class on the kinetic theory of matter. The first question here is extracted from June 2004, number 2. State 2 assumptions of the kinetic theory of gases. We all know that. The first one, gas molecules move randomly in straight lines colliding with one another and with the walls of the container. 2, the collisions of the gas molecules are perfectly elastic. 3, the volume occupied by the gas molecules is negligible. That is, they are very small relative or compared to the volume of the container. 4, the cohesive force between the gas molecules are negligible. That is, the force holding the gas molecules is very, very weak or small. 5, the temperature of the gas is a measure of the average kinetic energy of the gas particles. Now, please take note of this. You know, there will be questions on why is this that the real gases does not obey the assumptions of the kinetic theory of gases. The assumptions of the kinetic theory of gases is only meant for ideal or perfect gas. The real gas deviates from this law. The real gas does not, let me quickly point out the 2 laws. Only few of these laws obey the real gas. 2 of these laws are not, cannot be applicable to the real gases. The first one here is that the collision of the gas molecules are perfectly elastic. No, for real gases that we all know, the particles of the gases does not really collide with themselves. They are together, though they are not in solid form. So their collision is not perfectly elastic. They are not though they move, the particles move about, but the collision is not perfectly elastic. Then the number 2 law that the real gas does not obey is the number 2 as a theory is that the actual volume occupied by the gas molecules themselves is negligible relative to the volume of the container. That is, real gases have volume, they occupy space, and they have volume. Their volume is the volume is not negligible. They are not small. You know, most times we can fill gases, uses a gas cylinder. We fill gas inside the gas cylinder as big as like 50 kg, 100 kg. It shows that real gases have volume. So the assumptions of the kinetic theory of gases meant for the ideal or perfect gas, but not for the real gases. Now, number 2 questions. Which of the following phenomena lead to decrease in the volume of a liquid in an open container? Now, the first option here, please always read through your options before answering your questions and think carefully before selecting the best answer. The first option here is Brownian motion, the second one is diffusion, the third one is evaporation, and the fourth one is sublimation. Which one leads to decrease in the volume in the container? Brownian motion, no. This only shows the movement of particles. Diffusion also shows the movement of liquids and other particles through each other. Then evaporation is a solution, is a state whereby vapor or water particles escape into the atmosphere. And the fourth one here is that there is a change from solid to gas directly. So I think the best option here is evaporation. When evaporation takes place, particles of water escape, reducing, because the particles of water escaping is actually the water itself which has turned to vapor, thereby causing a reduction in the liquid of the container. That is the answer here. The best answer here is option C. The next question, the pressure exerted by a gas is a function of what? A, the total volume of the gas. That is the pressure that is created by the gas as they collide with themselves is a function of what? A, total volume of the gas, speed of the gaseous molecules. Is it the mass of each gaseous molecule or the frequency of collision between gaseous molecule? I think the best answer here is D. That is, when the gaseous molecules collide with themselves, they generate pressure, which I've explained under the kinetic theory of matter. Then the next one, the vapor pressure of a given volume of liquid increases. How does the vapor volume increase? When the liquid becomes saturated with a salt? No. The volume of the liquid increases? No. That is the pressure generated by the particles of the liquid increases when what? C, the temperature of the liquid falls. D, the temperature of the liquid rises. I think this D is the best answer, because when you increase the temperature of a liquid, the particles begin to collide with themselves and with the wall of their container because they've gained kinetic energy. And I told you that when you increase in temperature of a liquid or a gas or a solid increases the kinetic energy of their particles, making them to collide with themselves. And I also taught you earlier that when particles of these substances collide with themselves, they generate a kind of pressure, a vapor pressure, especially in boiling. So the best answer here is option D. Always check carefully your options, read through all the options before you choose the best answer. Then number 5 question here, which of the following statements about volatile liquid is true or is correct? Volatile liquid, actually, they are liquid that evaporates or escapes into the atmosphere. They vaporize easily. I'm going to give you some instances. Assuming you have petrol and you have oil, you have kerosene, which one is more volatile? Petrol is more volatile. We know that when we expose petrol, it dries up easily, just like methylated spirit, like an alcohol. They dry up when exposed, even without eating them or using them. Kerosene also does that, but kerosene, the rate of evaporation of kerosene is slow compared to petrol. And oil experiences little or no evaporation. So when a substance escapes or evaporates, they say they are volatile. So which of the following statements about volatile liquid is correct? 1, high vapor pressure and low boiling point. High vapor pressure and high boiling point. Low vapor pressure and low boiling point. Then low vapor pressure and high boiling point. I think the best answer is high vapor pressure. When the vapor pressure is increased because the particles have gained kinetic energy, they collide with themselves, generating a high vapor pressure. And when they generate this high vapor pressure, they begin to break through and they escape. And this high vapor pressure is actually brought about by high boiling point, that is increase in temperature, which makes the particles to escape into the atmosphere. That is the best option here is option B. Then state 2, postulate of the kinetic theory of gases. Which real gases do not obey? State 2 postulate of the kinetic theory of gases. Which real gases do not obey? This question has been answered. I gave you two. The collision of the gas molecules are perfectly elastic. No, real gases does not obey this. The actual volume occupied by the gas molecules themselves is negligible. That is very small compared to the volume of the container. No, real gases does not obey. There's the last question here. Explain briefly why real gases do not obey the postulates. The real gases are the gases we see around us. They do not fit into the picture of the ideal or perfect gas, which has various assumptions, which is the kinetic theory of gases. The real gases they have volume, they occupy space, and their collisions are not perfectly elastic. Though they collide with themselves, they do not fit into the picture of the perfect or ideal gas. They are real gases, and that is why they do not obey the postulate of the kinetic theory of matter or the kinetic theory of gases. And the chemical properties of these ideal gases are postulated by they are postulated by Graham's law of diffusion, whereas the physical properties are postulated by Charles Boyle's law, Dalton's law of partial pressure, and all this explains more about gases that doesn't really exist. They are not real. They are not real. They are just a perfect or ideal gas, how an ideal gas behaves, which backs up the theory of the Charles law, the Boyle's law, the Graham's law of diffusion, and the Dalton's law of partial pressure. This brings us to the end of the class. I must commend your efforts for staying through to the end of the class. Watch out for the next topic, which is on the changes in the state of motion. Thank you.